So I'm going to go ahead and use this time to go through the practice problems and talk about my solving process and see how it goes. So question number 1, what is the Euclidean space of the set of vectors? So this here would be R4. We've got our fancy R script. It means a set of real numbers, and there's 4 of them. So each vector has 4 numbers, so it's R4. What are the coordinate unit vectors of that space? So these are the vectors that define essentially the axes. So the y-axis and the x-axis, obviously in 4 dimensions. We can't really visualize it, but we can still write our coordinate vectors. So the first one has a 1 in the x and 0 everywhere else. So that's E1. E2 would be 0, 1, 0, 0, so it has a 1 in the y. E3 would be 0, 0, 1, 0, and then E4 is 0, 0, 0, 1. So these define our different axes in our 4 dimensions. Determine the unit vector of V1. Okay, so V1 looked like that. The unit vector, the equation for unit vector is V over the norm of V, or the length of V. So the length of V is Pythagorean theorem extended to however many dimensions. So negative 4 squared plus 0 squared plus 3 squared plus 0 squared. If I was writing this on paper on my exam, I'd probably write 16 plus 9. But square root of 16 plus 9 is a square root of 25, which is 5. So there's the norm. So therefore, UV is going to be negative 4 divided by 5, 0 divided by 5, or just 0. 3 divided by 5, and 0. So there's my unit vector. So I'll go ahead and highlight all my answers. And then we have determine whether V1 and V3 are orthogonal or not. So remember, in order for 2 vectors to be orthogonal, the dot product between them needs to be 0. So I'm going to take V1 and V3 and do the dot product. Give me half a second. I'm going to go ahead and pull up the final exam next to me so I can see all of it at once. Okay, so V1 dot V3. So V1 looked like that vector right there. I already wrote it down. Dot V3. V3 looked, oh, that's nice, convenient, full of zeros and nines. The dot product, I'm going to go ahead and multiply all these together and then add them all. So 0 plus 0 plus 0 plus 9. So the vectors are not orthogonal because V1 dot V3 is not equal to 0. Okay, so I've determined whether or not they are orthogonal or not. Orthogonal means they're perpendicular, just as a note. What is the distance between V1 and V3? So the distance between 2 vectors can be defined as the norm of the vectors minus each other. So that's our equation for distance. Between 2 vectors, you should have all of these equations written down on your sheet, on your on your cheat sheet. There we go. So we've got V1 again minus V2, which is 0, 6, 0, negative 8. So this gives me negative 4, negative 6, 3, and 8. So the norm of that is the square root of all of them squared. So 4 squared plus 6 squared plus 3 squared plus 8 squared. So this gives me, oh gosh, 1, 3, 6, that's 100, plus 12, 16, 25, square root of 125, which might be, I can simplify that in other places, but this will be sufficient. So there we go. That's the distance between those 2 vectors. Using the determinant, determine whether the set is dependent or independent. So this is use the determinant. So I'm going to go ahead and place all of my vectors into a matrix. And find my determinant, which in order to do that, I'm definitely going to use column 3. And honestly, it does not matter which order you put them in. As long as they're rows, columns, doesn't matter. You can put them out of order. Either way. So I'm going to go ahead and use this column to do the determinant. So I have to find C, let's see, this, I have to find this C. So C row 4, column 3. So that's going to be a minus there for my cofactor. Remove the row, remove the column it's in. -4, 0, 3, 0, 6, 0, 4, 6, -3. I can use whichever method I want to find the determinant. I can do cofactor expansion on a row or column as well. I'm going to go ahead and use the shortcut method because I have zeros and I think a lot of them are going to show up. Oops. Messing my rows up. 0, 6, 0, 4, 6, -3. So then I've got So over here I have -4 times -3 times 6. Which is 72 plus 0 plus 0. And then this way, nice. I have 4 times 6 times 3, so minus 72. So this ends up with my determinant being 0. My determinant is 0, therefore my vectors are dependent. Woohoo! My vectors are dependent. Because my determinant is 0. If my determinant is 0, that means they are a linear combination of each other. That means 2 of my rows or columns are effectively the same, which you can see in order to get this column here, you can see I literally more or less add the other columns together in some capacity. Okay, so they're linearly dependent because my vector or my determinant is 0. So based on your answer to F, can the set of vectors be written on as a linear combination? Yes. Yes, that's it. It asks, can it? It doesn't say you have to write it as a linear combination. It just means you can write it as a linear combination. Which, if I was going to write it as a linear combination, it would be V4 equals V2 plus V3 minus V1. That's what it would be. What is the space spanned? So we did not talk about space. The space spanned by them, V1 and V2, would be R2. But we didn't talk about spanning space, so do not worry about question H. And that's problem 1. Various equations, you saw them in one of the tables in the note sheet for week A. So go ahead, write down all those equations, understand what space means, understand what the coordinate unit vectors are, understand what a linear combination is, how we can use that to determine whether vectors are independent or dependent. So it's a combination of week 1 and week E that we had, or week A and week E. Okay, number 2. Problem number 2. Given the linear system, determine whether the system of equations is consistent or inconsistent. If consistent, how many solutions? So essentially it's asking me, solve it. So I can solve it however I want. Does not matter. However, if our system has infinite number of solutions or no solution, then the fastest way to get to the final answer would be using Gauss elimination. So I'm going to go ahead and use Gauss elimination. So I'm going to write my augmented matrix. And I'm going to do my row operations. So I'm going to go ahead and make that a 0 and that a 0. So to do that, I'm going to say row 2 equals row 2 minus row 1. And then row 3 equals row 3 minus 3 row 1. So I'm going to draw my little chicken scratch on the side so I can keep track of how I am doing this. And then down here, so 3 minus 3, 2 minus 3, -1 plus 3, and then 1 plus 3. Which gives me row 1 doesn't change. Row 2 now becomes 0, -1, 2, and 4. And then row 3 becomes 0, -1, 2, and 4. And notice my last 2 rows are the same, so this one will go to 0. Because I can say row 3 equals row 3 minus row 2 to get this last 0. Okay, which means all of it goes to 0, so I have zeros all the way along the bottom. So that means the rank of A is 2. That means the rank of AB is also 2, which means my system is consistent. It means I'm going to have an infinite number of solutions, which wasn't necessarily asked, but I'm just stating. I'm going to have an infinite number of solutions. My final REF will look like this. 1, 1, negative 1, negative 1, 0, negative 1. Oh, make those, switch those signs. This is my REF. I prefer RREF for an infinite number solution, so I'm going to go ahead and make that a 0, which I didn't need to change my signs. But I'm going to say R1 equals R1 minus rho 2. So I get 1, 0, negative 1 minus 2 is positive 1, negative 1 minus negative 4 is positive 3, 0, 1, negative 2, negative 4, 0, 0, 0, 0. So this is RREF. And you don't need to do this in order to get to infinite number solutions. I did it because then I can immediately jump to my solution right here. I can easily see that x1 equals 3 minus x3. And x2 equals negative 4 plus 2x3. So I can immediately jump there. But you could have done the same thing with RREF, or with one REF. Yeah. Okay, so determine that solution. So here's my solution. This is sufficient. You can also write it with, it does not say write it with an arbitrary parameter, but if it did, I would rewrite it as 3 minus t, negative 4 plus 2t, and t, where t is my arbitrary parameter for x3. Okay. It does say verify your solution. To verify your solution, just plug it back into the system of equations. So we have x1 plus x2 minus x3 equals negative 1. So 3 minus x3 is x1 plus, I will do it in terms of t, just less writing. 3 minus t plus negative 4 plus 2t minus t equals negative 1. So I can see t, those cancel, gives me negative 1, correct? So negative 1 equals negative 1. I can plug in the next one. 3 minus t plus t equals 3. That cancels. 3 equals 3. Yep, that's correct. And then my last one, 3 times 3 minus t plus 2 times negative 4 plus 2t minus t equals 1. So if I expand this one out, 9 minus 3t minus 8 plus 4t minus t equals 1. Negative 3t, 4, that cancels. 9 minus 8 is 1 equals 1. There we go. I have verified my solution. So I just plugged it into each system, or each equation in my system. Okay, so we have a consistent system because the rank of A over here, rank of A is 2. The rank of AB over here is 2. And that 0 row goes all the way across. I have an infinite number of solutions because I have a 0 row, because my rank is less than my number of equations I have. We found our solution and we verified it. Problem number 3. Given the following system of equations written in the form of ax equals b. So this is a weird way to see it, but really we just have 3 b vectors. So here's, you can think of b1, b2, b3. But this is still a. This is our first x vector, second x vector, third x vector, x1, x2, x3. But it's really just 3 systems of equations. Determine the inverse of A. Okay, finding the inverse of A, you have 2 options. You can do Gauss elimination with Gauss elimination, or Gauss-Jordan elimination, or you can use the inverse by finding the cofactors. I prefer the cofactors. So I'm going to go ahead and find all my cofactors. C1, 1. Remove a row, remove a column. Remaining elements is 1, 1, 0, negative 2. This cofactor. C1, 2. Remove the row, remove the column. Write my remaining elements. C1, 3. Remove the row, remove the column. Write my remaining elements. And then I just find my pattern and keep going. So note for each one, I'm removing the row 2, column 3, writing down my remaining elements, and then to find the sign, I go ahead and add the 2 and 3 together. And if it's even, it's a plus. If it's a odd, it's a minus. Or you can do your grid. So notice it's plus, minus. It alternates as we go along. I will eventually solve for these numbers. I just like to get the pattern down. 2, 1, 2, 1. These ones have the same row, same column, so I immediately know that's 0 using my shortcuts. This is a triangle matrix, so my determinant is just the sum of the elements along the diagonal. Same thing here, diagonal matrix or a triangle matrix. So that one's going to be positive 2. Same thing, 1. This one is neither of those. So that is a negative 2 there. So this one, I just have to actually do it. So negative 4 minus 1 is negative 5. If I change the sign in that, it's a positive 5. This is a triangle matrix. This is a triangle matrix. This is a triangle matrix in the other way, but it's a negative. This is a triangle matrix the other way, so it's also a negative. There we go. Got all my cofactors. So 0 minus 1. Here's 0 minus 1. Yes. Okay, which means I need to find my determinant of A. So I can use any cofactor now, any row, any column. So I will use column 1. So 2 times negative 2 plus 1 times 5 plus 0 gives me negative 4 plus 5, or 1. Such a convenient determinant, which means A inverse is just 1 over 1 times the cofactors transposed. So negative 2, 2, and 1 is my first row, so that's my first column. 5, negative 4, negative 2 is my second row, so that's my second column. Negative 1, 1, 0, third column. There's A inverse. Determine the inverse of my matrix. I could remove my fraction out front because it's not really a fraction, but it's also fine if you write it as a fraction out front. If I want to verify that it is the inverse, then I just need to do my multiplication. So I'm going to go ahead and write A down. I'm going to multiply that by my A inverse. And I should get identity. Okay, I should get identity. I know what my answer should be. So this requires matrix multiplication. So multiply, or dot product between row 1, column 1. I get negative 4 plus 1, which gives me 1. Check. That one's correct. And then I just keep going. These ones, negative 2 plus 0 gives me 0. And then keep going. 0 plus 2 minus 2 gives me 0. Okay, so that's the first row is correct. Then I move into the next row in the next column. And so I'll just highlight the column. So I get 10 minus 8 minus 2, which gives me 0. 5 minus 4 plus 0 gives me 1. That's what I expected. 0 minus 4 plus 4 gives me 0. And then I move into the next row in the next column. Notice this is verify. You can't just write down identity. That doesn't show us that you know how to do the multiplication. So at minimum, do what I'm showing you here. So negative 2 plus 0 gives me the 0. Next one, negative 1 plus 0 gives me the 0. And 0 plus 1 plus 0 gives me the 1. So here I can see I get identity. So I've verified it. That's my verification. Lastly, use the inverse matrix to determine x. So x equals A inverse times B. And this is true even if we have 3 x's and 3b vectors. So still the same. So A inverse is this. Go ahead, write down my B vector. And do my same multiplication. So row 1, column 1, I get 0 plus 5 plus 2, which is 7. I'll write my answers in a separate matrix down here, just because I'm running out of room. And then I get the next row, first column, I get 0, minus 4, minus 2, or negative 6. 0, minus 2, plus 0, or negative 2. There we go. That's my first x vector that I solve for. And then I move into my second column. So you think about it as, okay, I've solved one system of equations. Now let me solve the next system of equations. So for this one, I get negative 4 minus 5 plus 0. Okay, yep. Which gives me negative 9. And then 4 plus 4 plus 0, which is 8. 2 plus 2 plus 0, which is 4. And then my last system of equations with my last b vector, I have 6 plus 0 minus 1, so 5. And then negative 6 plus 0 plus 1, which is negative 5. And negative 3 plus 0 plus 0, which is negative 3. So there we go. There's my answer. Here are my x vectors. Capital X. No, you can verify that. You can go back, and if you do A times your x vector, you should get your b vector. So you can always verify your answers if you have extra time. So if I do A times x, I should get b. I'm not going to do that because I don't have time. But it's just more matrix multiplication. So the faster you are at these procedures, the faster you're going to be at your exam, which means you have more time for verification, more time to check your answers. Okay, question number 4. Notice these are 4x4s. The largest you will have on your exam will be a 4x4, and we will not give you a 5x5 or bigger. So just noting that. So you may notice that matrix A1 and A3 are obtained from A by changing one column only. So if we look at that, we can see that here column 1 is changed from A. And in this one, we can see that column 3 is changed. Determine the determinant of matrix A by expansion on the row or column of least computation. So least computation would be the one with the most zeros. So I'm going to go ahead and find my determinant using row 3. So, which means I need to find one cofactor. So my determinant of A is going to be negative 2 times one cofactor times C. That's row 3, column 1. So negative 2, that cofactor is going to be a positive number. If I remove the row, remove the column, I write my remaining elements, 0, 0, 2, 2, 2, negative 3, and negative 3, negative 1, 2. Multiplication. So if I find the determinant of C3, 1, I'm going to use cofactor expansion on this row. So if we keep going, then we have positive, or 2, this is C3, or 1, 3. So it will also be a positive number. Remove the row, remove the column, write my remaining elements, 2, negative 3, 2, negative 1. Once again, the faster you can do determinants and cofactors, the faster you're going to find your way through your exam as well. So my determinant of A is going to be negative 2 times negative 2 plus 6, which is 4. 4 times 2, negative 16, right? 4, yeah, negative 16. Okay, so that's my determinant of A. 1. 2. Using the determinant properties without expansion, find the determinant of A1 and the determinant of A3. Which of these determinants, which of these matrices are invertible? Okay, notice the difference between A and A1 is column 1 is multiplied by negative 3. So if my column is multiplied by negative 3, then my determinant is also multiplied by a negative 3. So that would be 42. Determinant of A is 42, A1 is 42. If I look at A and A3, I can see that... How are they the same? How are they similar? I can see that column 1 and column 3 are multiples of each other. So I can see these ones, they're the same. They're literally the same. Where column 3 is just column 1 multiplied by 3. So note, I have 2 columns that are the same. They are identical columns. Therefore, the determinant of A3 is going to be 0. That was one of our properties. If you have identical rows or identical columns, your determinant is equal to 0. So just because it's multiplied by a constant does not mean that it's not the same. Because if I just divide that by 3, I get column 1. And the determinant times 3 or divided by 3 is still 0 if my determinant is 0. Okay? So, which of these is invertible? Therefore, A1 and A are invertible. A3 is singular. Okay, using the determinant properties, find 2 times A1 inverse. So the determinant of A inverse is going to be 1 over the determinant of A1. So A1 inverse, so 1 over 42. If I multiply that by 2, then will also be multiplied by 2 4 times. Because it's for every row or every column. So each column is multiplied by a constant, therefore the determinant is multiplied by that constant for every single column. So that's 2 to the 4th, which is 16 over 42, which would be 3. I really hope all these answers are right. Determinant of A times A1 is going to be the determinant of A times the determinant of A1, which is negative 16 times 42. You can multiply that by hand on the side, or with a non-graphing calculator that you are allowed to have. Determinant of 3 times A1, come on, A1 is going to be this determinant up here times that matrix, whatever A times A1 is, whatever that matrix is, the determinant is going to be 6. I should probably do this. Negative 42 times 16, 12. You guys probably learned different. My son's learning things different. 24, 25, 4, 20, 2, 7, 6, 72. Something along those lines. If I do that matrix with a determinant of 672, and I multiply that matrix by 3, then my final determinant is going to be 3 times 3 times 3 times 3 times 672. So whatever this number is. I should probably have the answers pulled up next to me just to verify that things are correct. But that is the logic. That's a large number. Give me half a second. Microsoft Word decided it would open up over on that screen. There we go. Did I read it wrong? Oh, I totally read it wrong. It's not A. It's A inverse. Okay, make sure you read your exam. A inverse, not A1. I totally did my math incorrect as well. 48. There we go. 48. 3 times 6 is 18, not 12. Fun fact. Which means this is times 48. Which means this math is incorrect. And we'll just erase it and pretend it doesn't exist. And just write it like this. Negative 16 times 48. Okay, so last one. 3 times A inverse. So A times A inverse, this here would be identity. The determinant of identity is 1. So I would do 3 times 3 times 3 times 3 times 1. So it would be 3 to the 4th, which is 3 cubed is 27. If I multiply that by 3, I get 81. There we go. There we go. Now we're on track. We are doing great. It's hard for determinants because you can't verify unless you actually do the matrix multiplication, which for 4x4s, it becomes a bit cumbersome. So make sure you have your determinant properties listed out for you on your cheat sheet. So there's, once again, a table of properties that I gave you guys in week C notes. So make sure you pay attention to those. And make sure you read your exam paper. Pay attention to A1 versus A3 versus A inverse, because all of those things are different matrices. Okay, moving on to the next one. Ooh, we got 2 more questions. We're moving through this real quick. It'll be fine. You'll have plenty of time. 2 hours, you'll have plenty of time. It'll be great. For the following linear system, here we go. Write the system in form of AX equals B. So if it says write the system in the form of AX equals B, go ahead and make sure you write it in the form of AX equals B. So not the augmented matrix, not as a linear combination, as a AX equals B. So back to week 4 material. So A looks like 1, 0, negative 2, 3, 3, negative 2, 5, 0, 0, 2, 4, negative 3, and then 0, 0, 0, 2. I have 4 unknowns. So I've got my x vector and my b vector. There we go. There's AX equals B. Determine the LU factorization of matrix A. No permutations are required. Okay, so I don't need a P matrix. So I just need to do my row operations using only elimination to get to REF for my A matrix. So I need to get that 3 as 0. And I can only do it by saying row 2 equals row 2 plus some multiple of row 1. And then the zeros below that, so get the 0, 0. So row 3 equals row 3 plus some multiple of row 1. That's going to be 0. And row 4 equals row 4 plus some multiple of row 1. That one's also 0. So this one is going to be negative 3. So if I do that, I get 3 minus 3, negative 2 minus 0. 5 plus 6, 0 minus 9. And I'm only looking at my A matrix. I do not have my B vector in there. So row 1 does not change. Row 2 becomes 0, negative 2, 11, and negative 9. Row 3 doesn't change because I did not have to multiply row 1 by anything. Or multiply row 1 by 0, and then row 4 doesn't change because I multiply row 1 by 0 in order to get those to be zeros. So I've got my zeros in column 1. Now I'm going to go ahead and get my zeros in column 2. And I can only use these row operations. Row 3 equals row 3 plus some multiple of row 2. Row 4 equals row 4 plus some multiple of row 2. So those are the only options. Those are my only options. So I need to figure out these constants. So this would be a 1, and that would be a 0. So row 1 doesn't change. Row 2 also doesn't change. Row 3 now becomes 0, 0, 15, and negative 12. And then row 3 becomes 0, 0, 0, 2. And then my last one is get my zeros in column 3. So I can only say row 4 equals row 4 plus some multiple of row 3, and that multiple is 0. Okay, so I've gotten to U. Here's my U matrix. Woohoo, go me. I will verify this. Make sure I'm following the right answers. Okay. I need to put L together. So L, so there's U, so I need L. We'll put L down here. L starts out looking like this. Since we don't have permutations, constructing L is really simple. It's 1's long diagonal, 0's in our upper right, and then I just slot in the opposite, so the negative number of what I used in my row operations. So I have a 3, a negative 3, so it would be positive 3, and then 0, and then a 0. Then a negative 1, and then a 0, and then a 0. I can call them negative 0, but I changed the sign. So in order to get my zeros in column 1, I use these multipliers. In order to get my zeros in column 2, I use these ones, and then those ones. And note they are negative. They are the opposite sign. Okay, so here's U and here's L. Write the elimination matrix E21. The elimination matrix E21 is identity. If I can actually write identity without messing it up. But in the 2-1 position, I'm going to go ahead and put in the multiplier that I used for eliminating the 2-1 location. So here is that row operation. So I put the -3. This is where the negative comes into play. L is full of the inverses, so it's a +3. But in E21, it's the number, it's the raw number. It's the -3. And then lastly, solve the system equations using LU factorization. So I need to say Ly equals B, and then Ux equals Y. So let's go ahead and find Y first. So I take L. Then I have Y, and that equals my B vector. -7, oops, equals. Forgot the other side of my equation. And then I just solve it using forward substitution. So here I can see y1 equals -7. If y3 times y1 plus y2 equals 4, or y2, this is -21, so plus 21 equals 25. Y0, y1 minus y2 plus y3 equals 11. So y3 is plus 25, so 36. And then lastly, I can see y4 equals -6. So here are my y values. So then I have ux equals y. So u looks like this. X equals my y values, so -7, 25, 36, and -6. Yeah, you go me. And I solve this using back substitution. So I start with my last one and work my way up. So here I can see, I'll work down here. x4, 2x4 equals -6, or x4 equals -3. So there's my first unknown. 15x3 minus 12 times x4 equals 36. So this is 36, so minus 36, so x3 conveniently ends up being 0. Woohoo! In general, for your exam, you will have whole numbers or very small fractions. Unless it's Cramer's rule. If it's Cramer's rule, anything goes. You can have any fractions you want because you're just finding determinants. But if you have to do row operations and everything, where you have to keep track of things as you go along, you are going to have small fractions to deal with or whole numbers. So this equation, I can see that -2x2 plus 11x3 minus 9x4 equals 25. So that goes away. This is 27, so minus 27. So x2 ends up being, so that's -2, ends up being 1. And then from the last equation, we can see that, let me write it up here, x1 plus 0 minus 2 times x3, which is 0 plus 3 times x4 equals -7. So this is -9, so plus 9. So x1 ends up being +2. And there we go. We have solved the system of equations using our L and U. And you can write this neater. You can see that y, I ran out of space, but we can see y equals -7, 25, 36, and -6. And we can say that x equals 2, 1, 0, and -3. However you want to write it, as long as we can clearly see your answers and we can clearly see your work, then what I wrote is fine. Writing it as vectors is fine. Doing the interchanging, writing them both ways is fine. Just make sure we can follow your work and we can actually see your final answer. Okay, last problem. Problem number 6. So eigenvectors and eigenvalues and all that fun stuff. So I have one matrix. I have 1, 2, 3 eigenvectors and 3 eigenvalues. Woohoo! Makes my life a little easier. Make sure you pay attention to how these questions can be asked. This is not comprehensive, so please use your homework problems as an additional guide to understand how the different problems can be asked for each type of solving mechanism, each week of material. Which, for example, there's no Cramer's rule problem on here. So once again, it's not comprehensive. So find the values of Q, R, and S such that x1, x2, x3 are eigenvalues of matrix where we have the corresponding eigenvalues. So note the eigenmatrix or eigenvector problem is this. So if I do A times x1, Q11, that should be the same as saying 0 times x1. That's a Q, not a 9. So if I actually do this multiplication, I can use any row or any column I want. Where I can look at those ones, I can say negative 4Q, that's a Q, minus 7 plus 3 equals 0, Q, or equals 0. So this means that negative 4Q minus 4 equals 0, or Q is going to be negative 1. I will write that a little bit neater, make sure we know it's a Q. Q equals negative 1. And then I just repeat for my remaining ones. There's A, there's x2. And to be honest, you only need one row or one column of A, or one row of A, because when you do the dot product, if I would find the same thing regardless of which row and which column I use to find the dot product. So that's lambda 1, so that equals negative 9R. So once again, do the dot product between the two, I get negative 16 minus 35 plus 3R equals negative 9 times 4, which is negative 36. So this is negative 51, so plus 51, I get 3R equals 4, 5, 15, or R equals 5. And then one more. For S3 equals 7 times x3. So once again, the dot product, I get negative 16 minus 7s plus 9 equals just this first number. Just remember, first row, first column, make sure you're only setting it equal to the first number. Okay, if you are using one row or one column, if you're only using one row of A, because make sure you understand all these mechanisms. Equals to 28. So I get negative 7s equals minus 9 plus 16. So this here is positive 6. So 34. No, that's not a 6. It's not a 15. This is positive 7. So it'd be 35. So S would be negative 5. Okay. So there we go. I found all my eigenvectors. I found the missing values. Asks, is the matrix diagonalizable? Yes. Because my eigenvalues are distinct. So if I look at eigenvalue 1 equals 0, it's not equal to eigenvalue 2, which is equal to -9, which is not equal to eigenvalue 3, which is equal to 7. They're distinct. Therefore, it is diagonalizable. Using the determinant state within the matrix of eigenvectors is singular or invertible. Okay, so I know my vectors are independent, which means my determinant is not equal to 0, but I have to show that. So, what was cute? -1, 1, 1 is my first eigenvalue vector. 4, 5, and 5 is my second eigenvector, and 4, -5, and 3 is my third eigenvector. So, once again, I can use whichever method I want. I'm going to use my shortcut method or my modified fish method. So over here I get -15 minus 20 plus 20 minus this one I get 25 plus 12 plus 20. -15 minus 57. So it's -72. My determinant is 72, -72, which is not equal to 0, therefore they are independent. Eigenvectors. Okay, without calculations, write down the product of x inverse a x. This will be equal to capital lambda, which is my diagonal matrix with my eigenvalues along the diagonal. So, note, it says x is in this order, x1, x2, x3. Therefore, my lambda needs to be in that order. My capital lambda also needs to be in that order. So if x1 is in column 1, lambda 1 is in the 1, 1 position. If x2 is in row 2 or column 2, then lambda 2 is in the 2, 2 position. And if x3 is in column 3, then lambda 3 is in the 3, 3 position. So there is my product. Did I answer all of them? Yeah, I think so. Okay, so there we go. We have finished the practice exam. Once again, it is not a comprehensive list of topics, nor a comprehensive list of solving techniques. This practice exam was pretty heavy on the determinant. There weren't that many row operations. So make sure you do review row operations. We could have found the inverse here using row operations. I used cofactors because I find them to be take up a smaller amount of space and to be less prone to error. But that's one place where we could have had more row operations. We did have row operations for LU factorization and for this problem here. Notice this problem did not tell you how to solve your system, so you could have tried to use Cramer's rule, but no, Cramer's rule would have broken down because your determinant of A would be equal to 0 because you have an infinite number of solutions. So just pay attention to how important understanding row operations are, how important it is to find cofactors and find the determinant. And yeah, I think that's it. That's what I got. Okay, so hopefully you find this video useful. Please, please, please also review your homework problems as alternative ways questions can be asked. Okay, so good luck on the final.